So here we've got initial value problem. Now we can see here that y at 0 equals 2 and the first derivative at 0 equals 6. So that denotes an initial value problem, and we've got a second order linear differential equation here, y double prime minus 4y prime minus 5y equals 4. Now y in this case is a function of t, and that's what we're going to try and find, our y as a function of t. Now for the technique to solve this on this video, I'm going to use Laplace transform. Now that's a really nice way of solving these second order linear differential equations. Now some of the stuff in this video has been acquired in previous videos, which you'll see in the link below. So first of all, we need Laplace transforms of the first and second derivatives. So the Laplace transform of the first derivative, so that is s times the Laplace of y minus y at 0. So that's the first thing we need to know. Now the next one is the Laplace transform of the second derivative. So if I just write that like that. Now this one is a slightly extended version of this one. That gives us s squared and then Laplace of y. That's how we get the second derivative out of Laplace. And then from that we subtract s times y at 0 minus the first derivative at 0. Okay, so that's our building blocks for now. So what we're going to do now is substitute the transforms into this second order linear differential equation. Okay, so y double prime, that's using this one. So give myself a bit of space, I'm going to start over here. So I've got s squared Laplace of y minus s times y of 0. So that's s times y at 0 is 2. So that's going to give me 2s. So I'm going to write that as 2s. And then minus the first derivative at 0. So that's going to be minus 6. So that takes care of this one. Now I want 4 times the first derivative. So now minus 4, so I'm going to need a bracket here. And then I'm going to need to input this one. So we've got s times the Laplace of y, and the function at 0 is worth 2. So that takes care of that. And then for 5y, I'm just going to input Laplace of y for that. So minus 5 times the Laplace of y, and that equals 4. Okay, now for the 4, I need the Laplace transform of 4. So I'm going to change this into the Laplace transform of 4. So for any constant, so the Laplace transform of a constant k, that just gives me k over s. So s always has to be greater than s0. So a little condition here, I'm just going to write s is greater than s at 0. For this to work and this technique to work, that's going to have to happen. So here I've got k over s, so I'm just going to rewrite that as 4 over s. So therefore I've Laplace transform both sides. Okay, now let's just work on some algebra on this side and see where that takes us. So this I can just leave as it is, s squared Laplace of y, minus 2s minus 6, I'm going to leave that like that for now. And then I'm going to just FOIL out this minus 4 with both of these terms. So I'm going to have minus 4s Laplace of y. And I'm going to distribute the minus 4 with the minus 2, so that's going to give me plus 8. And this one here, going to leave that as it is, minus 5 times the Laplace of y, and that equals 4 over s. Okay, right. Now I can see here my goal is to find this Laplace of y in the first instance. So I can see I've got 1, 2, 3 terms with the Laplace of y. So I'm going to factor those terms out on the left hand side of this equation. So if I take out the Laplace of y, and then next to that I've got s squared, that's the first term. The next one I've got a minus 4s, and here I've got minus 5. So in this stage you know you've gone right on this kind of question if you've got something that looks similar to what this is. So the powers of s determine which level of derivative, and you'll have a minus 5 because that's 5 is the constant with just a function. So that should take care of that. And then I need to fill in the rest of it. So I've got minus 2s, so I'm going to have to put that in. And now I can just simplify out my two constants here. So minus 6 plus 8, that's going to give me plus 2. And then, so that takes care of all of that. So that just equals 4 over s. Okay, right. Let's move this stuff onto this side. So now I'm going to have 4 over s plus 2s and then minus 2. And this is just going to be the same. So I'm just going to write that as Laplace of y s squared minus 4s minus 5. Okay, my next level of working, I'm going to try and factor this out. I can see that can be factored. So I'm going to do that next. But first of all, I'm going to sort out this side here. Now I've got 4 over s here, but these have got no denominator. So I want to get s in my denominator here so I can write this as one fraction. So for that, if I multiply that by s over s and multiply this term by s over s, I will get something with just s on my denominator. So if I write this like this, the 4 will stay. So to multiply this by s over s, I'll have 2s squared over s. So that's plus 2s squared. And then minus 2 times s over s, that's minus 2s. So there's the s there, that's to go with it. Okay, now this one here will stay, but I'm going to factor this one out. So now I've got Laplace of y times, so factoring this one out, I'll have s minus 5 and s plus 1. So minus 5 times plus 1 will give me minus 5, and then minus 5 plus 1 will give me minus 4. So I'm happy with that. So that would be good there. Okay, right, now to get Laplace on its own, I'll just divide both sides by this term here. So now I will have Laplace of y equals 4 plus 2s squared minus 2s. I'll keep that s there, and then these two expressions will come down next to this s. So now I've got s minus 5, s plus 1. Okay, so now I've got something now which is looking after taking care of this Laplace transform. So what I want to do now is clear some space on the board, and let's see if we can deal with this into something we can do an inverse transform. Okay. Okay, so now to break this apart, we're going to need partial fraction decomposition. Now there's a link in the description below as to how we did partial fraction decomposition of this function. So to save time on this video, I've done it on a separate video, and the link will be in below. So the result of that partial fraction decomposition, that gave us minus 4 over 5s, so that's the first part, plus 4 over 3s plus 1, and then plus 22 over 15s minus 5. Okay, that's what our result was. So now we've got something now, we can do the Laplace inverse transform of these three expressions here. So minus 4/5 with s in the denominator, that looks something like this. So here I've got my constant k, which could be minus 4/5, and I've got my s in my denominator. So that going the other way around will just give me the constant k. So this is minus 4/5. So minus 4/5, that takes care of that. Now this one here, this is going to be the exponential function. So now if we look at the Laplace transform of an exponential function, k e to the at, that gives us k over s minus a. So if we go the other way around, we'll get our k and our a, and the t is our dependent variable, so that's where we need the t. So now k for this one is going to be 4/3. So I can add 4/3, and then that will leave me 1 over s plus 1, so that will give me a minus 1 for my a. So therefore I've got e to the minus t. So that takes care of that term. And now this one here, similar thing going on. This is going to be an exponential function as well. So I'll have a k of 22 over 15. So 22 over 15. And the exponential function with my variable t. And here I've got s minus 5. So therefore my a is 5. So that is the result of our second order linear differential equation initial value problem using Laplace. Now I'm just going to simplify this off a little bit just to make it a little bit more palatable. So give everybody the same denominator. So I'll have to multiply this one by 3, so that's minus 12. Multiply this one by 5, so that's plus 20 e to the minus t. And then that one can stay, plus 22 e to the 5t. So now just writing that with the 1/15 taken out. So 1/15. And then I've got to write this minus 12 further to the end. So I've got 22 e to the 5t plus 20 e to the minus t minus 12. And I'm happy with that as my solution to this initial value problem. Okay.